First of all, my warmest thanks to the organizers. And I believe my story today perfectly fits the title of the event, because I will be talking about how the 65 years old concept of condensed matter, namely Anderson localization, Anderson transition, meets quantum information. And this will happen in platform of free fermions under random measurements. So the story is described in those two preprints, where the main actor is Igor. So I will start with a brief introduction, thanks to Michael. Yesterday, Michael Buchholz already introduced the topic of measurement-induced phase transitions. And then I will jump to the field theoretical approach and show how measurement-induced transitions are related to Anderson localization. And then I will discuss one-dimensional free fermions under measurements. And I will show you that there is no measurement-induced transition for free fermions in dimension 1. And at the end of my talk, I will discuss systems, free fermionic systems in dimensions above 1 dimension. And there is entanglement transition induced by measurements. And this transition is very similar to the Anderson metal insulator transition. Okay, so this is the setup. We have a one-dimensional Fermi gas governed by this hopping Hamiltonian on the lattice. So this is our chain. And from time to time, randomly, with a given rate per site, we measure the occupation of random site. So the result of this measurement, this is a projective measurement, strong measurement, is a collapse of the wave function such that the bit string corresponding to the many-body wave function has the entry 0 or 1. So no electron, no fermion, or 1 fermion on this side. No click of the detector. And the probability of getting click or no click outcome of the measurement is given by the standard Born's rule. So this is just the expectation value of the projector operator, which projects either on 0 or 1 for the occupation of a given site. So we do it randomly in time and in space. What one gets is this density plot. So this is the evolution of density at given point and given time. And here the rate of measurements is small. So the evolution of the system is mainly governed by the system's own Hamiltonian. And the density stays around 1/2. Here you see some rare spots that are positions of measurement events in space-time. Now, with increasing the strength of the measurement, you get a more contrast picture, and for very frequent measurements, the system does not evolve. So we observe quantum Zeno effect, because if the site occupation is 1, then when you measure it frequently, it stays 1. So this is the picture of illustrating the density evolution, and this should be somehow related to quantum information and through the entanglement characteristics of the system. And we will see that indeed for free fermions, the standard characteristics of entanglement in a system, the entanglement entropy defined in the standard way with the subsystem A and all other degrees of freedom traced out, it can be related to full counting statistics of the particle number in the subsystem. Right? So in the subsystem, you can have occasionally 1, 2, 3, 10 fermions. Well, not more than 7 here in this case, because of the Pauli principle. And the entanglement entropy for free fermions, or more generally for Gaussian states, can be expressed in terms of a series of cumulants of the particle numbers. So, and this is a celebrated formula by Clich and Levitov that connects counting statistics and entanglement entropy, and it can be used to calculate the entanglement entropy because in many cases the series can be stopped at the first term. So in order to calculate a very nonlinear quantity, the entanglement entropy, one can calculate the cumulant, the second cumulant, which is just quadratic in the density matrix. So this simplifies calculations. So what's important here is that all those quantities are nonlinear in density matrix. So when we average over quantum trajectories, over positions, times, and outcomes of measurements, the product of two observables, each of which is linear in the density matrix, we do not get a product of averages. And this complicates the calculations. So what can one expect from the behavior of the system under measurements? So this competition between the unitary and non-unitary measurement-induced dynamics may lead to emergence of volume law phase when the entanglement entropy grows as the volume of the subsystem. And this is typical for generic excited states in the Hilbert space. The entanglement entropy can show the area law being proportional to the area of the subsystem in 1D is just a constant. Or it can be critical, it can have some logarithms. So this area law is typical for states with finite correlation lengths, gap states, and critical scaling is typical for gapless states. And for example, at 0 temperature, the ground state of Fermi gas is characterized by this behavior because there are some power law correlations in Fermi gas. And this is typical, and this is the standard result for conformal field series. So the question is, what are the phases for free fermions and are there phase transitions between those phases? So there have been long discussions in the literature, arguments between various groups. So some people found numerically and had some phenomenological arguments in favor of single area law phase, no transition, just like in a gap-full system. Free fermions, monitored free fermions, and no transition. So other people found transition between a logarithmic critical phase and the area law phase at a very frequent measurement. So in the limit of frequent measurements, everybody believes that there is quantum Zeeman effect and entanglement entropy does not depend on the subsystem size, showing the area law. So, this is a very nice analytical work by participants of the event who developed a field theory for free Dirac fermions under continuous monitoring. And Michael Alex and co-authors predicted a transition between a logarithmic phase and area law phase, similar to this, in terms of utilizing an effective Latinger liquid description, such that the CFT, conformal field theory, central charge in the log phase was found theoretically smaller than 1. And I should also mention a recent work by those two groups who developed a field theoretical nonlinear sigma model approach for monitored Majorana fermions. And in particular, Fava and co-authors found a transition between a critical but log squared phase and area law phase. So the whole zoo of results, no transition, but all those works have something in common. There is no volume law for free fermions. Okay, so let's try to analyze this problem step by step. So for this, we introduce a non-normalized density matrix that describes the evolution along the quantum trajectory. So these are random positions, times, and outcomes of the measurements. So between consecutive measurements, this density matrix evolves by unitary operators governed by the system on Hamiltonian, and at the measurement event, this density matrix E is projected by the corresponding projectors depending on the outcome. And the normalized density matrix, so at each step, the state of the system along the quantum trajectory is a pure state. So measurements, it's a pure state and it's still Gaussian state. So we can normalize the density matrix at the very end of the procedure. And the Born's rule is expressed in terms of the trace of this density matrix. So this is just the normalization of density matrix. And this allows one to, this is important for the consideration of nonlinear functionals of the density matrix, for which we introduce n copies of the density matrix. So we have the density matrix raised to the power n, because we want to average something like this. And what's important here is that the probability of having given sequence of measurement outcomes is again the trace of this d. So this is rho raised to the power n, and this is the trace of d is the probability, Born probability of having given quantum trajectory. So this is trace of d to the power raised to the power 1 minus n. Now we introduce R replicas of the system. So we write here R instead of 1 and take the limit R to 1. So this is just the same, but this allows us to average just a product of R copies of the system's density matrix. And the replica limit for finding the observables here is R to 1. This is the replica limit. Okay. So we use the replica trick, but it's unconventional. So it's different from the one uses for studying Anderson localization, where the number of replicas is set to 0. Okay, so these are the correlation functions that we are calculating. So they are matrices in the replica space. The diagonal in replicas correlation function describes the average density, and it's governed by the conventional Lindblad equation, Lindblad type equation for the average density. But this correlator does not tell us anything about particle number fluctuations and entanglement entropy. For so the correlation function of main interest is this replica of diagonal correlation function. And you see in this term, so this would produce the second cumulant and the first term in the expansion of the entanglement entropy. And you see here, we average 2 copies of the system. Yeah, so that's why we need the replica trick. Right, so with all this, skipping technical details, we arrive to a nonlinear sigma model, which turns out to be very similar to the one describing disordered systems. And this nonlinear sigma model has 2 sectors, a replica symmetric, generating those boring correlation functions, and a replicon sector, which has this SUR symmetry. And the replica limit R to 1 will be taken at the end of the calculation. So the replica symmetric density correlation function, just average density, is diffusive. So it diffuses, yeah? So it's characterized by just diffusive propagator, conventional diffusion. So average density, it spreads diffusively, goes to 0, goes to homogeneous limit, even in the limit of very strong measurements. This is because you average over those pictures with quantum zero. When you average over them, you would get 1/2 everywhere. So this corresponds to infinite temperature heating, because so we wait, we measure the system for a long time, and each measurement event changes the energy. It excites the system. So at long time, the whole band of the entire band of fermions on the lattice will be populated by many body states. So it's effectively infinite temperature on average, but as Mikhail mentioned yesterday, the particular wave functions still have interesting correlations inside. And those correlations are captured by this replicon sector of the nonlinear sigma model, which is D+1 dimension. So it combines space and time. So for 1-dimensional chain, we get a 2-dimensional sigma model. And density fluctuations encode Anderson localization of information in D+1 dimension, as we'll see from this theory. Okay, so we can calculate the correlation function without quantum fluctuations at the Gaussian level. It's for 1D is given by this formula. So what the important object here will be the Fourier transform of this function. It would be convenient for determining transitions later. So the second cumulant is expressed in terms of this Fourier transform of the correlation function. It's just the integral of the correlation function over space, and it behaves logarithmically in 1D. So we observe at the Gaussian level critical logarithmic behavior. So it's in between the area and volume laws. But this is without quantum corrections. This is analogous to the Drude conductivity in disordered systems. But we know that there are quantum corrections that can localize the system or make it supermetallic. And those corrections are conveniently derived from the nonlinear sigma model in the theory of Anderson localization. So this is the Lagrangian of our nonlinear sigma model, and the renormalization for this chiral sigma model is known since long ago. Hikami and Wegner calculated 4 to 5 loops of the beta function. We need only the first loop here. So the effective coupling constant here that plays a role of the conductance is governed by this beta function. R is the number of replicas and the sign is negative. So G decreases upon renormalization. What does it mean? So this G enters the cumulant. So the cumulant is proportional to G. And when G goes to 0, this cumulant also decreases, right? So, and so does the entanglement entry. So with this, so the theory flows to strong coupling like conventional two-dimensional Anderson localized system. Yeah? So all states are localized. For weak disorder, the localization length is exponentially large, and here the correlation length is also exponential function. For weak disorder, exponentially large. So beyond the scale, one would expect an exponential decay of correlators, meaning the area law beyond this L correlation. So this is because of weak localization. And I should mention that in those parallel works studying Majorana fermions, monitored Majorana fermions, the symmetry was SOR. So, and this is because the particle number was not conserved for Majorana fermions. And the sign of the beta function was plus. So G grows, and at large scales, G is logarithm. And this is weak anti-localization, and you get log squared. But for normal fermions, we have Anderson localization of information here. Okay, and this is seen in numerics. So this is how this Fourier transform behaves. So you can infer from it the nature of the phase. So if C of Q over Q diverges as 1 over Q, you get volume law. So there are no such curves here. So if it has a constant limit at 0 Q, then you get a critical log law. And if it goes to 0, you get area law. Yeah, for very frequent measurements, you get this area law for nothing. But it turns out, oh, wrong way. Turns out that all curves eventually go to 0 for one-dimensional free fermions. Yeah, and they go up first, following this ballistic curve, reach a maximum, and then go down. And this is just the weak localization correction. Yeah, so if we subtract, so the difference between the curves and this Drude curve is shown here, and this is just the weak localization correction, which basically follows this predicted behavior. Yeah, so for very frequent measurements, it saturates, but this is clear because the correction cannot be larger than the main term. Yeah, so the conductance cannot be negative. All right, and here the entanglement entropy is calculated numerically, and here the ratio of the entanglement entropy and the second cumulant is shown, and you see that even in the limit of strong measurements, the ratio basically follows this constant connecting the first term, the entanglement entropy, and the first term, second cumulant in the Clich-Levitt formula. So even strong disorder does not, apparently does not break this relation. Okay, so this is 1D. And now, in the remaining 3 minutes, I will show the results for 2D systems. So the field theory is the same. The quantity of interest the quantities of interest are the same. Again, the second cumulant and the entanglement entropy, and the indicator of the transition of the phase would be the same correlation function C of Q. Now in the D-dimensional case, at the Gaussian level, we get system size to the power d minus 1. This is sub-volume law times logarithm. Right? So the critical behavior of the entanglement entropy for gapless phase is this. Yeah, so for d equal 1, it's just logarithmic. Okay, and with this sigma model, we can derive the RG equations for the dimensionless conductance and the cumulant, second cumulant. So we first solve this equation and then use the solution here to calculate the second cumulant. And you see that when d is equal to, or more precisely, when d is larger than 1, so already at the level of 1 plus epsilon, we observe a critical point at one loop. So this term is positive, this is negative. This critical point means that for d larger than 1, there is a transition at some critical value of the measurement frequency. And this transition has much in common with the Anderson metal insulator transition in dimensions d larger or equal to 3. So for rare measurements, we get this metallic law, area times log, and for frequent measurements going to the quantum Zener limit, we get this area law. So the same conclusion was simultaneously, concurrently drawn in this paper by Mikhail and his students. Right. So now, what about the connection? Yes. Last slide. What about the connection between Anderson localization and quantum information? It turns out that this so if you introduce the setup with two leads of finite size attached to a two-dimensional system here, you can ask the question, what is the conductance in this setup? And this conductance is expressed through the same correlation function that we calculated. So this conductance is the average particle number covariance, and through this Clich-Levitt formula, we connect this conductance with the mutual information of those two subsystems. This is just inequality. So this is just from definitions of mutual information and the relation of entanglement entropy and particle number cumulants. And with this formula, we predict the scaling of the mutual information. So in the metallic case, it grows with the subsystem sizes. At the critical point, it's given by this critical conductance, GC, it stays constant. And in the insulator, it decays exponentially as correlations in Anderson insulator. So this is a direct link between quantum information and Anderson localization. So This is what we got numerically for 2D. We extracted the critical point and the corresponding exponents. Exponent of the correlation lengths. I will not go into detail, so this is a summary of my talk. So, measurement-induced entanglement transition is about Anderson localization of quantum information. In 1D, there is crossover between logarithmic and area law phase, similar to localization crossover in two-dimensional disordered systems. No transition for one-dimensional systems, only area law phase is possible. And in D larger than 1, there is a phase transition between area times log and area law phases, reminiscent of Anderson transition in disordered systems. Thank you for your attention.